Okay, so let's begin. So how is the preparation going on for NSEM?
It's going on fine.
Okay. So we'll have 4 revision sessions. We'll do weeks. We'll try to cover weeks 1 to 4 today, and we'll set the pace depending on how you want it to. So we'll start off with week 1. So the course started by studying about vectors, right? So we started off with vectors in R2 and R3. How did we represent elements in R2?
XY along the plane XY.
Yeah, you wrote it as an ordered pair. So it
Ordered.
is a pair of elements and there is an order that is followed. So if I write x first, it means that x is the first coordinate and y is the second coordinate. And in R3, we had 3 components, x, y, z. So how did we add vectors in R2 or R3?
Addition of 2 vectors was coordinate wise addition. Each coordinate of the vector is a coordinate.
So addition was component wise. So x1 plus x2, you add the first components of both the vectors, comma, add the second component of both the vectors. And then we had seen scalar multiplication. How did we multiply a vector with a scalar?
Each coordinate by the by alpha.
Yeah. So each of the component was getting multiplied by the scalar. So these are the operations that we had seen on vectors in R2 and R3. And this is what generalized into a general vector space later on during the course. So after this, after vectors, we had seen what matrices. What is a matrix?
It's an array of numbers arranged in
Yeah.
rows.
Yes, it's an array of numbers arranged as rows and columns. So suppose the matrix has m rows and n columns, so it will look like this. You have m cross n, m into n elements arranged in a rectangular array of m rows and n columns, and the order of the matrix is represented as the number of rows cross the number of columns. So we write the number of rows first, m, and then the number of columns cross the number of columns, m cross n, and an m cross n matrix has m into n elements. So you can, how do we associate vectors with matrices is that you can see each column of the matrix as a vector or each row as a vector. So you can see them as vectors as well, as a set of vectors put together. And how do you add 2 matrices? When can you add 2 matrices?
When
The same dimension.
Same dimension.
Yeah, when both the matrices are of the same dimension, only then you can add them together. And how do you add?
to represent dimension, we say order
Component
of
wise.
Yeah, the order of the matrix, yes.
Component wise.
Yeah, every you add the corresponding components, and the sum is going to be the matrix, which is got by adding the corresponding components of the first matrices. So how I add is that I add the first component here with the first component here. C plus G, D plus G, right?
Yes.
And how did scalar multiplication work?
All elements.
Yeah. So if I multiply a matrix with a scalar, what I do is I multiply each of the elements with the scalar. Okay. And we had what is called as matrix multiplication. How did matrix multiplication work? When can we do matrix multiplication?
Number of columns of the first is equal to number of rows of the second.
Yeah. So if I have a matrix of order m cross n, and another matrix of order n cross p, that is the number of columns of the first matrix is equal to the number of rows of the second matrix, then I can multiply these two matrices. And how did I multiply?
Row of the first matrix into the column of the second
in the
matrix.
column.
A plus B,
Yeah.
A plus BG. And then
And
AF
AF
plus
plus
BH.
BH.
BH. Then CE plus DG. Then CF plus DH.
So this is how you did matrix multiplication. So what we had predominantly seen was 2 cross 2 means of orders 2 and 3 mostly. Means either we hadn't seen big matrices. That's it. So this is how matrix multiplication is defined. This is not the usual way we multiply, so we need to be careful about this. You take the first row of
Ma'am, I have a doubt in vector. I think we just now we covered vector and then move to matrix, right?
Yeah.
May I ask the question?
Yeah. Sure,
Ma'am,
sure.
Ma'am, what is the difference between a point and a vector? Like in coordinate geometry, when we started learning coordinate geometry for the first time, so we used to locate a point by saying, say for example, a 2, 3, right? So it means a point is located 2 units away from x-axis and then 3 units in the y direction, right? So what is the difference between point and a vector, ma'am?
This was already discussed in one of the live sessions, right? Because
Okay.
I remember because it was discussed in
Sorry,
mine.
then I will
So
explore.
a point.
I will explore, ma'am. Okay.
No, I'll just tell it quickly now. So if you write this 2, 3 as a point, you mark the x coordinate y. This point is a point, and if you want to write it as a vector, you give it a direction in the sense that it is this vector which starts at the origin and ends at 2, 3. So this is the vector 2, 3, means when you represent this as a vector.
Vector has magnitude and direction, correct?
Yeah, it has a magnitude and direction. And point is just that point in the plane.
Correct.
Okay. Okay. And then after matrix multiplication, what is the transpose of a matrix?
Which the columns and
Columns and rows get interchanged. I mean, rows become columns.
You interchange the rows and columns. So if A is, I'll fix A for this 2 cross 2 here, A, B, C, D. So A transpose would be A, B, C, D written column wise, right?
Yes, sir.
Yeah. Okay. So and then what did we know? Determinant. What is determinant of a matrix?
Expand the matrix with respect to any row.
So the determinant is a fixed number that is associated with a matrix.
Correct.
If I have a 2 cross 2 matrix, say A, B, C, D,
Correct.
what is its determinant?
A into D minus
BC.
minus BC.
AD minus BC.
Yeah, the determinant is AD minus BC. So you multiply the diagonal elements minus the off diagonal elements. So the determinant of a 2 cross 2 matrix is easy to compute, AD minus BC. If I had a 3 cross 3 matrix, how would I compute the determinant?
Then we have to expand it with respect to any row.
Yeah. So in this case, what you do is you choose one particular row, say any row, and then you do some operations, right? So suppose I fix the first row, I will take the first element of the first
Usually
row.
we take first row, right? Or
yeah, it's based on convenience. But suppose the last row has 2 zeros and 1 1, then that is the easiest row to choose, right? But in general, we choose the first row. Yeah. So what you do is you take the first.
right? Sorry.
What is it?
Answer won't change for any row. I mean, if we take any row.
No, the determinant is a fixed number. Irrespective of what row you choose, you will get the same number. Okay, so you take the first entry of the matrix and then you remove the corresponding row and column. So whatever is left out, the 2 cross 2 portion that is left out, you just find the determinant of that part. So EI minus
Ajam.
FH.
Yes.
And then
Minus
the first entry of the first row is over. Then minus, the signs alternate. You take the second entry, B. So you remove the row and column from where B comes, and then take the determinant of the remaining 2 cross 2. BI minus GF. And then take the third entry, remove the row and column from where it comes, as C times determinant of the remaining 2 cross 2, DH minus EG. So this is how you calculate the determinant of a 3 cross 3 matrix by expanding along the first row. Okay.
Yes.
In general, when I want to expand it along any row and any column, for that I need to know what is actually this portion, the little portions that we are getting here. So that is when we introduced minors. What is a minor?
It is a part of the matrix.
Part of matrix where you said that if you fix any first row, then EH, EF, and HI becomes the minor of that matrix. Means
Yeah.
if I'm fixing
Okay,
it.
so suppose we have A11, A12, A21, A22. What is the minor corresponding to A11?
A22.
A22.
Yeah, why is it A22?
Because you have fixed with respect to A11, we have removed first row and first column, and the remaining
Yeah.
element is A22. So that will be the minor.
Yes. So the minor of any element is nothing but remove the row and column where it appears, and whatever remains after removing the row and column where that element appears, whatever remains, you find the determinant of that portion. So if it's a 3 cross 3 matrix, the minor of an element would be determinant of a 2 cross 2 matrix, right?
Yeah.
If it's a 4 cross 4 matrix, then the minor of any element would be the determinant of a 3 cross 3 matrix, right? Because when I remove a row and column corresponding to it, I'm reducing the size of the matrix by 1.
Yeah.
So the minor of A11 here would be A22. The minor of A21 would be
A20.
yeah.
A12.
Similarly, the minor of A12 would be
A21.
A21. Yeah. And the minor of A22 would be A1. In the 3 cross 3 case, A13, A23, A31, A32, A32. So what is the minor of A11 here?
A22, A23, A32, and A33.
Determinant of
Determinant.
A22, A23, A32, and A33.
A3.
Yeah.
A22.
You take the determinant of this matrix. Yes. And what is the minor of A22? A12?
Determinant of A21, A23, A31, and A33.
Yeah. And similarly for A13, it would be the determinant of this portion. So this is what we did while finding the determinant of the entire
It is an absolute
matrix,
number,
right?
right? It is an absolute number, right?
It is. What do you mean by absolute number?
Like whatever number we will get after multiplication and solving that number. We don't put any sign while calculating minor. We don't put any sign, right?
Yeah.
Okay.
So it's just the determinant of that 2 cross 2 portion that you will get. These are the minors corresponding to the entries in the first row, right?
Correct.
Yeah. Okay. So then we had the concept of cofactor. What is a cofactor?
Is the minus the sign.
Yeah. Cofactor is nothing but a signed minor. So minus 1 power I plus j into minor of aij. Right?
Yes.
You take the minor of aij and then you multiply it with minus 1 power I plus j.
I and J
So
are
if I
the
take,
row column, right?
yeah, so whatever is that, my matrix is Aij. So this is my matrix A11, A12. I and J represents the row and column. The position is based on which row and which column it appears. So what is the cofactor of A11?
So it's the minor without
Minor itself.
Minor.
Yeah. What is the
1%.
cofactor of A12?
minor.
Negative of minor.
Negative of
Yeah.
determinant.
Yeah. So
Ma'am couldn't
at
get
all
the point.
these,
A1.
okay. Why A1? You understood the minor of A12, right? How to find the minor of A12?
Yes.
You remove this row, this column, whatever is remaining, the 2 cross 2 matrix, take the determinant of that.
Okay.
But when I want to calculate the cofactor, I also multiply it with this minus 1 power I plus j, right?
Okay.
What is I here?
1.
For A12?
Yeah.
1.
And j is?
2.
Is 2. Okay.
Yeah, it appears in the first row and second column.
First row.
So
Okay.
first row, I is 1, j is 2. So this is 3, I plus j is 3. So minus 1 power 3 is minus 1, right?
Okay.
Yeah. So the sum of the indices, I plus j is what matters, right? So when the sum of the indices is odd, you will be multiplying the minor with a minus sign. And when the sum of the indices is even, you will be multiplying it with a plus 1, right?
Okay.
Yeah. So at all these positions, the sum of the indices is odd. So the minus corresponding to these 4 elements will have a minus 1. Multiply with the minus 1 to get the cofactor. Whereas the ones in these positions where the sum of the indices is even, your cofactor will actually be equal to the minor, right? So the sign is this: plus, minus, plus, minus, plus, minus, plus, minus. You find the minor and then you see the position of the element that you're looking for, and then multiply by whatever, means change the sign. Multiply by plus 1 if it is a plus, multiply by minus 1 if it's a minus, to get the corresponding cofactor.
We can directly change the sign based on this convention, sign convention. I mean, if we
Yes.
have calculated the minor, then.
Yeah. This is nothing but I'm getting this plus and minus based on this, right?
Yes, ma'am.
Yeah. I plus j, wherever the position the positions where I plus j, that is the row index plus the column index is odd, you will have a minus sign. That's it.
Yes.
So while expanding the determinant, can you see that I'm multiplying A with the cofactor corresponding to A. I'm multiplying B with the cofactor corresponding to B. And I'm multiplying C with the cofactor corresponding to C.
Yeah.
Yeah. So in general, the determinant of a matrix can be calculated by multiplying an element with its cofactor. Means take a row, fix a row, and then take all the elements in that row and then do this.
Ma'am, here it will be minus
So this,
A12.
no, it will be plus because the cofactor will give me the minus sign. Right?
Yes.
Not. Ma'am, can you take
If
an
I had
example?
written minor, if I had taken minor, I would have written minus A12. But because I'm taking the cofactor itself will give me a minus sign, right?
Can you take an example of any matrix?
Yeah. So what is the determinant of this matrix if I expand along the first row?
6.
Okay, so I will do 1 into the cofactor corresponding to 1. What is the cofactor corresponding to 1?
0.
0.
It's the determinant of 1, 0, 1, 0. I remove this row, this column, right?
Yes.
And then as per this definition, it's going to be plus
Plus
2 into the
One.
cofactor corresponding to 2.
In bracket -1 and then to the power 1 plus 2. Yes.
1 plus 2 I'll have.
Yes, then you will
2,
understand.
0, 0, 0. And then A13, that is 3 into the determinant of 2, 1, 0, right?
Ma'am, here you have taken this -1 to the power 1 plus 2. Why? Because it is negative. I mean, we.
Yeah, everywhere I will have that, no? The cofactor is -1 power I plus j. So this is 1 plus 3. Here it is 1 into -1 power 1 plus 1. This is the cofactor corresponding to 1, right?
Okay.
This is the cofactor corresponding to 2. This is the cofactor corresponding to 3.
Okay. Okay.
Yeah. So you can find the determinant by expanding along any row or any column. So it doesn't matter which row you choose. You can even choose columns corresponding. So I can do the same thing. Say for example, I expand along the first column. So that's going to be A1, 1 into cofactor of A1 plus A2, 1 into cofactor of A2, A3, 1 into cofactor of A3. So in this matrix, expanding along the third column is the easiest, right?
Yes.
Okay.
2, 0 are there.
Why?
Yeah,
Because
because
0 are there.
Because 2 of the entries are 0, so I just have to multiply this number with its cofactor, right? What is
Yes.
the cofactor of this element?
2.
It's going to be -1 power. The position is first row, third column. First row, third column into determinant of 2, 1, 0, 1. So this is positive plus 1 and this is 2. So the cofactor corresponding to this entry is 2. So what will my determinant be?
3 times 2.
6.
3 into the cofactor corresponding to 3, 6. So my determinant is 6. But I can expand along any row, any column, you'll get the same answer. So here we have expanded along the first row. Here it is 0, 0, 2, 6. You expand along any row or any column, you will get the same number, which is the determinant of the matrix. Fine?
Then it means if I expand along first row or any row or any column, my determinant will not change. 6. I mean.
Yes. For this matrix, it's always going to be 6. If it's going to change, then there is no concept of a determinant, right? Because the determinant you get may be different from what I get. So it's a fixed number. That is why it is nice. Okay. So what do we know about determinant of A transpose?
It's going to be
Same
Same
as
as the determinant of A.
Yeah, it's going to be the same as the determinant of A. And then what do we know about determinant of product of two matrices?
product of the determinant.
Determinant of A times 2.
Yeah. So these things we will be using often. And what happens if, before that, what happens when we do row operations on the matrix? How is my determinant going to be affected? If I interchange two rows, what happens to the determinant?
Negative of determinant.
Fine.
Yeah.
Row
Interchanging rows, sign changes.
determinant sign changes when we fix.
Yeah, the sign of the determinant changes. So all this is row operation, this is effect on determinant. So the sign changes. So if I interchange two rows, my sign of the determinant changes. If I do two interchanges,
It becomes positive.
so the determinant of this matrix and the determinant of this matrix. If I already know the determinant of this matrix, what will the determinant of this matrix be?
-6.
-6.
-6.
Minus.
What will the determinant of this matrix be?
-6.
6.
6, no? I have interchanged two rows from this matrix.
Again the sign changed.
Yes.
Yeah. The sign changes again, or if you start from this matrix, you can see that there are two interchanges that has happened. The
But
first row
we
has become the
interchange-
second.
Ma'am, at every change, interchange the sign changes. I mean, if we interchange.
Yes, yes. Every time you interchange two rows, the sign gets multiplied by -1. Means the determinant gets multiplied by -1.
Yes.
Okay. So here I've done two interchanges. So because of which the determinant is not changed. In fact, the sign is changing twice. So from plus to minus to again plus. So the determinant doesn't change. Okay, what happens when we multiply a row with a scalar and add it with another row?
Determinant gets multiplied with the
It will
scalar.
multiply the
And determinant becomes 0.
Ma'am, if we
No, the determinant, yeah, if we
interchange column, then the determinant will be also be multiplied by -1.
yes, all these are what I've written down here is row operations, but it's the same effect for columns as well. You can also define column operations in a similar manner. Yeah. Okay, so what happens in this case?
Determinant gets multiplied with the scalar.
Oh, same.
No,
No change.
Oh, no change. Determinant doesn't change.
no change in this case. So what are you actually doing? So what is this matrix? 0, no, 1, 2, 3.
1, 2, 3.
2, 1, 0, 0, 1, 0. So what we are doing is, say for example, I do R1 as, I replace R1 as R1 plus 2 times R2. So I'll get 3, no, 4, 5.
5.
2 plus 2, 4,
4.
3.
3.
So what is the determinant of this new matrix?
6.
6.
Yeah, it's still 6. You can expand along the third column. That's the easiest. So it's still 6. So when you do this kind of a row operation, so you replace one row.
It should be 5 to 3. The first row.
First row?
Should be 5 to 3.
No, I'm adding the first row with 2 times the second row. So that's going to be 2 plus 2, 4.
Okay.
Right?
Yes, ma'am.
Now you're adding it to the first row, right? Sorry, the first column.
We are changing the first row.
First row. The first row is replaced with first row plus 2 times second row. 1, 2, 3 plus 2 times the second row. 4, 2, 0.
Right.
This is my new first row.
Okay.
Yeah. So when you do such operations, the determinant does not change. Why doesn't the determinant change in this case?
Because we have multiplied a row with a scalar and added it to another row.
Right, this is scalar multiple of another row.
Yeah, you're basically adding two matrices. 1, 2, 3, 2, 1, 0, 0, 1, 0 plus 4, 2, 0, 2, 1, 0, 0, 1, 0, right? You're basically adding these two matrices, right?
No, it should be 0, 0, right?
Where?
The second row and third row will be 0
All zeros.
of the second matrix.
If you add,
No, I'm only changing the first. Oh, okay, fine. Oh, no. Okay, I'm replacing only the first row. Okay, fine. Okay, then I think this is a bad way of writing. Okay, so what is actually happening here is that yeah, okay. So here you're doing R1 plus 2 R2. So you're adding, okay, I'll write it in terms of column operations. That will be easier. So if I'm replacing the first column with the first column plus 2 times the second column, what I'm actually doing is this is my new matrix, right? If I write it down as columns, right?
Yes.
So the determinant of this matrix, can be written as determinant of this matrix. 2, C2, C2, C3, right?
Yes, ma'am.
Determinant of this matrix can be written like this. What is the determinant of this matrix?
that will be 0.
Yeah, because I have a column which is a scalar multiple of the other. Yeah. So when you do such operations, you're always going to end up having something like this because you're taking scalar multiple of some other row or column. So when you do all that, the determinant is not going to be affected because in one of the matrices, you will have a scalar multiple of a row or a column. So here we are using 2 rows are scalar multiples of each other. Or columns. Implies determinant is 0, right? If I have 2 rows which are scalar multiples of each other or 2 columns which are scalar multiples of each other, the determinant is 0, right?
I think the first example which you wrote, that is also good. And I think is the first matrix have 2 rows as 0. Then I think the explanation.
Writing it as columns is easier. I could have written it like this. R1 is replaced with R1 plus 2 R2, R2 and R3. So I should write the matrix like this.
Yes, ma'am.
Right?
Yes.
Yeah. And then when I take the determinant, determinant of this matrix would be determinant of R1, R2, R3 plus 2R2, R2, R3. So this determinant would be 0, right?
Yeah.
Because 2 rows are scalar multiples of each other. So this determinant would be 0. I'll still be ending up with the determinant of the original matrix. Okay. So doing such row operations does not change the determinant. What is the one more row operation that we are allowed to do? Multiply a row by a scalar, right?
Yeah.
By a scalar, say C. Then what happens to the determinant?
The determinant
C
also gets
times
multiplied.
determinant.
So it's going to be C times the determinant of the matrix that you started with. So when you have a common scalar in a row or a column, just pull out that scalar, right? And then calculate the determinant. So these are the 3 row operations. And these are the row operations that are allowed when you do the row reduction and all that, right? These are the only ones that you're allowed to do, right?
Yes.
So you can, whatever row operations we discussed and whatever effect it has on determinant can be done for columns as well. These are not just for rows, but they can be done for columns as well. But we are interested only in row operations because when we consider the system of linear equations and all that, we are not allowed to do column operations. So that's why we study everything in terms of row operations. Okay, what happens to the determinant of a matrix with a 0 row?
Zero.
0.
Yeah, with a 0 row or a 0
Determinant
column.
would be 0.
Yeah, the determinant would be 0. So if you have 2 rows or columns which are scalar multiples of each other, the determinant becomes 0. If there is a 0 row or 0 column, even then the determinant becomes 0. So if you can bring it to those forms, then it's easy because you can just look and say that the determinant is 0. Okay, so this is with respect to determinants, minors, cofactors and all that. What about the inverse of a matrix? Okay, tell me one thing. Can I calculate the determinant of an m cross n matrix?
No.
Yes.
No.
M plus n.
No.
M cross
should
n,
always
yes, m cross n.
If it is
It should always be a square matrix.
Yeah. So when we talk about determinants, we are talking only about square matrices.
And what are we discussing?
Only then you can calculate the determinant. Okay. So if the determinant of a matrix is not equal to 0, the matrix is said to be invertible, right?
Yes.
And if the determinant is 0, it's a singular matrix.
Singular.
It is a singular.
What is it?
What are we discussing?
Yeah, it's a singular.
What disconnected?
What is it?
I mean, what are we
Yeah.
determinant?
No, I'm just telling that if the determinant of any matrix is non-zero, the matrix is said to be invertible.
Oh.
And if the determinant is 0, it's invertible, means singular or non-invertible. These terms are used to determine to tell that the matrix has determinant 0. Okay, so when the determinant of a matrix is not 0, we can talk about the inverse of the matrix, right?
Yeah.
Right? How will you find the inverse of the matrix?
You have to find the adjective which.
Find the minor and cofactor and then
Transpose of the cofactors.
Adjacent.
adjoint
1
of
by
it.
determinant of A into adjoint of A, right?
Yes.
And what is adjoint of A?
It is
Cofactor transpose.
cofactor transpose. Transpose of the
Transpose of the cofactor matrix. And what is the cofactor matrix?
Find the minor.
The cofactor matrix is the matrix, all of whose entries are the cofactors of the corresponding entries of the matrix. C11, C12, C13. Similarly, C31, C32, C3. Okay, I'll write the second place. Yeah.
Yeah, in that case, if a matrix is not a square matrix, then the inverse doesn't exist, right?
Yeah, because the inverse formula has determinant. No, the determinant doesn't exist if it's not a square matrix.
Yeah. Okay.
So the cofactor matrix is this, where Cij is the cofactor of Aij. Aij is the original matrix that we started, right? Okay, so the example that we took, 1, 2, 3, 2, 210, etc. 210, 010. The determinant that we calculated was 6. So is this matrix invertible?
Yes.
Yes, ma'am.
So can I find the inverse?
Yes.
Okay. So first let's find the adjoint matrix. For that I need the cofactor matrix.
Yes.
So what is the cofactor matrix?
Zero.
How will I find the first entry here?
1 times minor of 1010.
No 1 times. It's
What?
just
It's a
the
sign
sign
minor.
minor. You
Sign
don't
minor.
multiply with the number.
0.
It's because it's 0 because the determinant of this 2 cross 2 matrix is 0. What about this entry? How will I find this one out?
That is also 0.
0.
That's because the determinant of this matrix is 0. I have to also multiply it by a minus sign, but it doesn't matter if I multiply 0 by a minus sign. So, okay, fine. What about this entry?
2.
Yeah, it's the determinant of this matrix, 2. And then, what about this entry?
3.
3.
Is 0. Oh,
Yes.
no, I should eliminate this. Yeah, it's minus 3, but then I have to multiply it with a minus 1, so it's 3, right?
Yeah.
And then the next entry is
0.
1 into 0, 3 into 0. And this entry is
-1.
1 minus 2. So I have to multiply by a minus 1, minus sign, so minus. Okay. This entry
-3.
Okay. Next one.
6.
6.
And then last one.
-3.
-3.
Okay. So this is my cofactor matrix. So what will my adjoint matrix be?
Transpose.
Yeah. So what is my inverse?
Divided by 1 by 6
times adjoint of A.
1 by 6 times 0, 3 minus 3, 0, 0, 6, 2 minus 1 minus 1. So this is the inverse of the matrix that we started with. So is it clear how we find the inverse?
Yeah.
Yes, ma'am.
Can we multiply this machines?
Yeah.
When we multiply this one by
this also.
this element, element will be divided by 6 or only one row or only one row? Because
No, every element will get divided by 6.
scalar multiplication. Okay.
Yeah, you're doing scalar multiplication. This is the inverse. What is special about the inverse of a matrix? If I multiply the matrix with its inverse, what do I get?
Identity matrix.
We get the identity matrix. Okay. And what is the determinant of the inverse?
1 by determinant.
1.
1 by
1 by
determinant.
determinant of A.
Yeah. So this is a valid division because I know determinant of A is not equal to 0. Because if determinant of A was equal to 0, then there wouldn't be an inverse at all.
Yes.
Okay. So this is all with matrices. So then we had systems of linear equations. So what was this? What is a system of linear equations?
X equal to 0.
You have a system of equations. So x1 plus x2 is equal to 1, x1 minus 2, x2 is equal to something like this. When you have a system of linear equations, they all represent lines, right? This is the equation of a line, this is the equation of a line. So they are linear equations, and then you have a system of them. So how do you solve in this case? Usually what we learnt in school?
Algebraic method.
Yeah, what to subtract these two.
Elimination.
And then you'll get
Substitution.
equal to you eliminate and then you substitute. X2 is 1, so x1 is 0. So this is how we used to find the solution to the system of linear equations in school. But then we can convert this when we have a bigger system. Now that we know about matrices, we can convert this in a matrix form. So you can convert the system of linear equations in a matrix form like this. Ax is equal to b, where A is the coefficient matrix, x is the variable vector of variables, and b is the right hand vector. So how will this system be written as Ax is equal to b? What is my A?
1, 1 and 1 minus 2.
1 minus 2.
And then this is x1, x2 is equal to 1, 2.
2.
So if you multiply these two matrices,
we cannot keep x as minus 2, and either the x1 second equation somewhere problem. Otherwise, we will not get x2 is equal to 1.
Oh, okay. I think I did some calculation. Okay, 1 minus 2 it would be. So this would be minus 1 by 3. So this would be 4 by 3. Now is it right?
Yes, ma'am.
Okay. So we can write it as this system. So now when you multiply these two matrices, you're going to get this left hand part, x1 plus x2, x1 minus 2, x2. And I'm equating them as vectors. So we can write any system of linear equations in the matrix form like this. And then, so how do we deal with systems of linear equations after writing it in the matrix form? How can we solve them? Or what and all can we do?
Elimination.
Oh.
Yeah.
Gauss elimination.
So using this matrix form, we can talk about the solutions of the system of linear equations and all that. Okay. So one such rule that we learned to solve is the Cramer's rule, right?
Yeah.
What is the basic necessity for Cramer's rule to be applied?
Determinant should not be 0.
Determinant.
The determinant of the matrix
Square
should
matrix.
not be 0.
Should be square matrix.
Yeah, it should be a square matrix first of all, only then we can talk about the determinant. And the determinant of the matrix, the coefficient matrix, should be non-zero. The coefficient matrix should be inverted. If this happens, then how will I find the solution?
You replace the first column by
xi is going to be determinant of Axi.
By determinant of A.
Yeah. And what is determinant? What is Axi?
By replacing the first column by the B, by B.
Ith column, right?
no, ith column. Yeah.
Yeah, ith column, yeah.
Replace ith column of A by B. So in this matrix, I already know the solution for the system. What is it? Minus 4 by 3 comma minus 1 by 3 is the solution. So if I use Cramer's rule to find out, what should I do? What is determinant of A firstly?
Minus 3.
Minus.
Yeah. What is Ax1?
It is
1, 2.
1, 2, 1 minus 2.
What is the determinant of Ax1?
Minus 4.
Minus 4.
Minus 4.
Minus 4. What is Ax2?
1, 1.
1,
1, 2.
1, 2.
1, 1, 1. Yes.
Can you be
replace the
slow, ma'am?
second
Can you
column.
be slow? I'm not getting it, ma'am. Once again, x1.
Okay. AX1 is replace first column with the right hand vector. So that's going to be replace this column with 1, 2. So 1, 2, and then keep the second column as it is. 1 minus 2.
Yes.
Clear? And AX2 would be replace the second column with the right hand vector. So the first column would be 1, 1. The second column would be 1.
And this Cramer's rule is applicable only for square, right? So means determinant.
The condition is determinant should not be 0. So obviously it should be a square matrix. So is it clear how did we get AX2?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. And then what determinant of AX2? What is determinant of AX2?
1.
So what is my x1?
x1 by determinant of x1 by
AX1.
4 by 3.
So 4 by 3. What is x2?
Minus 1 by 3.
Minus 1 by 3.
1.
So this is what we had got even by the method that we used earlier, right? 4 by 3 comma minus 1 by 3. Same solution. So you can choose to do it in any way you want, but Cramer's rule in some, you would have seen certain problems where Cramer's rule is the only way with which we can solve. So there was some partial information given about the solution vector, some problem in practice assignment, right?
Mm-hmm.
So in those cases, Cramer's rule is helpful.
If there is a partial solution given to the in this system, we can apply this.
Yeah. Okay. And then after Cramer's rule, we had this row echelon form and all. So what is the echelon form?
I have one question.
Yes.
How they can ask, like they can tell a determinant first, and how they can say like what is the AX1, what is the AX2, how they can say.
I did not understand.
Let's assume.
Are you asking?
I'm asking regarding Cramer's.
Yeah.
Let's assume I have a matrix, and in that question they asked for the matrix determinant is -2, and AX1 here you are mentioning AX1. How they can say in the words what exactly AX1? AX1 determinant. AX2.
These and all cannot be put in words. So maybe
how they can phrase questions.
Cramer's rule is weak to it. So in this case, in this question, there's no way of putting AX1 in words. You can only tell like replace the first column of A with this vector or something like that.
Okay.
But when partial information about the solution is given, you can use Cramer's rule to get more information.
That's fine. I just want to know if there is any words to represent.
No. There's nothing in words that we can put for these matrices. Okay. What is an echelon form?
Reduce the matrix.
When do you say a matrix?
Converting it into the bonds and like creating a pivot around that.
Pivot element.
So when do you say a matrix is in row echelon form?
When all the rows are having leading entries, and each leading entry should be on the right side of the previous one, and all the non-zero rows should be above the zero rows.
Yeah, that's it. So the first condition is that every leading entry of the leading entry of every row will be done. The leading entry of every row should be 1. What do you mean by leading entry?
The first
Ma'am, every non-zero row, na? Actually.
First non-zero element
okay.
of that row. First non-zero element of that row is leading.
Yeah. So if you take a row, suppose it has a non-zero entry. Okay, only if it has non-zero entries, we can talk about the leading entry. So you want the first non-zero entry of every row to be 1. So that is what you mean by the leading entry. The leading entry means the first non-zero entry. That has to be 1. And then the second condition is that, what was the second condition?
Every leading entry in next row should be like
to the right
of
the
right of
all the elements below that leading entry should be 0. All the elements below that leading entry should be 0.
Yeah, that is what the second condition says.
Correct.
Yes. The leading entry of each row should be to the right of the leading entry of the previous row, right?
Yeah.
This just says that the entries below the leading entry of each column should be should be 0, right?
Correct.
That column.
If you have a leading entry here, everything else below it should be 0. That is when the next row's leading entry will be to the right of the previous, right?
Yes, ma'am.
Okay. And what is the last condition?
All the
non-zero rows
should be above the 0 rows.
Yeah. Put all the 0 rows at the end. That's it.
Okay.
All non-zero rows should be above the 0 rows. So the matrix that we started with, 1 0 0 1 0. Is this in row echelon form?
No.
No.
Okay. Is this in row echelon form?
No.
No.
Is this in row echelon form?
No.
No.
Why?
Because second and third row, one is appearing at the second position.
Yeah. So this is the leading non-zero entry of my second row. So any leading non-zero entry of the rows below it should be to the right of it. So this should basically be 0, right? Now is it in row echelon form?
Yes.
Yes. Yes.
Now is it in row echelon form?
Yes.
Yes.
Yeah. So all these are row echelon forms. What is, yes?
What about this last condition, like all non-zero rows should be above the 0 rows, right? So say for example, if in one of my matrix, if my 0 row is becoming the first row, so that won't be a row echelon form, right?
Yeah, this is not a row echelon form.
Okay, so I have to interchange it, right?
Yeah, I will interchange to make it to row echelon. So this is not in row echelon
So
form.
in that case,
Ma'am,
yes.
Ma'am, the condition that you have given, that's for reduced row echelon form, right?
No, no, this is row echelon.
So this is row echelon.
If it's reduced, I'll have one more condition.
The 2 should be 0.
Yeah,
All
this 2 should be 0. This 3 should be 0.
3 should be 0. Yes. Even 3 should be 0.
Okay, okay.
Yeah. So this is row echelon form.
Ma'am, but when I am interchanging my rows, then it is impacting my determinant. So won't that be, will that create any impact on my end solution?
No, see, it will definitely make an impact in the determinant. But when we are solving system of linear equations, we are not dealing with determinants, right?
Okay. Yes.
Yeah. Okay. And then what? Yeah. What is the reduced row echelon form?
The
All
entries are
entries other than pivot is 0.
also 0. Only the reading
Of a column, right? So firstly, it should be in row echelon form. And on top of that, I have the condition that whenever I have a pivot entry,
all the entries above pivot should be 0.
Above and below.
Yeah, actually your column should have only the leading entry, right?
The pivot entry, yes. The columns containing the pivot entry should have only the pivot entry, right? So is this in reduced row echelon form?
No.
Why? Because this is a pivot and the column containing this has another non-zero entry. So now this is fine, but still the third column is a problem. So this has to be 0. What about this? Is this in reduced row echelon form?
No.
No.
What about this?
No.
Why not?
Yes.
Actually,
Yes, it is.
What is the pivot for the first
no, it's
row?
not pivot, right? The last is not pivot. That should be at the
This is
end.
pivot. This is pivot.
And that does not appear.
So this is fine. What about this?
It is
This
okay.
is not fine.
No.
It
This
is
is
okay.
also fine, right?
Yeah. This is fine.
Because this is not a pivot.
Right.
Yeah. But if there was a 1 here, then it would be a problem.
Yeah, since the last row is not a 0 row.
Ah.
Now it is.
I didn't understand this, ma'am. Actually, in this case, is it in reduced row echelon form? It's not, right?
In this case, yes, it is.
Why? Because it is the last element.
Is it in row echelon form?
It's in row echelon form, but not in reduced row echelon form.
No. What is the pivot for the first row?
First row is the first one is the pivot.
Second row?
The again the 2 element, yeah.
Is the column containing the pivot having only the pivot?
Yeah, okay. The condition is the column should be having the pivot, then only it should be having only pivot. Okay, okay, got it.
Yeah. You cannot reduce it.
Yeah, this is fine. This is the final, no? This is already in reduced row echelon form, so you cannot reduce it further, no?
So, ma'am, in that case, since the last column is not having pivot, I need not reduce it further.
You cannot reduce it.
I can reduce it, no?
You cannot do anything further, right? Yeah.
Oh, yeah. Otherwise, it will not be in row echelon.
Yeah.
Okay,
This is the
got
final
it.
form, no?
Yeah.
Last row is
Thanks.
already 0.
But there is no pivot for the row 3.
Yeah, there's no pivot for row 3. It doesn't matter because it's a 0 row.
I have small doubt. What is the pivot?
Pivot is the first leading non-zero entry, the leading non-zero entry of each row. So leading non-zero entry means the first non-zero entry.
From the left to right, is it?
Yeah, from this way.
Okay.
Okay, so why is
should it not be a minimum condition to have a pivot in all the rows?
No, why is it necessary?
No,
you may have independent variables. No?
What is
you're asking if that is a condition for row echelon form? Is that what you're asking?
Yeah.
No. It is not. It is not necessary that every row should have a pivot.
Then what is the difference between a matrix with every row with a pivot and a matrix with no pivot in a row? Can we identify
the determinant will be 0. Invertible matrix. Every row has got
If you have a pivot in every row, the determinant will be non-zero. The determinant will in fact be 1, right?
Yeah.
And solution.
Diagonal matrix.
Solution. No?
Yeah, the
Determinant of the
solution will be
matrix.
unique.
Determinant of the matrix need not be 1.
No, if you have a pivot in every row,
Yeah.
it's going to be this, right?
Determinant of the final matrix will be 1, but the original matrix will be.
Yeah. Oh, not the original matrix. No. I was talking. Oh, okay. Sorry. Yeah. I was talking about this matrix, the final matrix. It will in fact be the identity matrix, right?
Yeah, that's the point I was about to ask. Okay.
If the matrix
So
is
the difference is
invertible,
if it is pivot in all the rows, then the determinant is it's an identity matrix. If not, it is not. It's not 1. It's different.
Means the determinant of the original matrix will be non-zero. That much I can tell.
Ma'am, in this case, if had the third column be having all zeros, then the determinant it's still in reduced echelon form, but the determinant will not be 1.
That is not possible.
Like this, yeah.
No, this is still possible. No, you can have this 1, 2, 0.
Oh, okay.
1, 2, 0.
Okay. Yeah.
In this case, you'll get this.
That's correct, Nana. That is still in reduced echelon form, right?
Yeah.
Even my third column are 0, it is still in reduced echelon form, right?
Yes.
Okay.
See, if your final row echelon, this reduced row echelon form is the identity matrix, it only tells you that the original matrix is invertible, right?
Yes.
Otherwise, this is not possible. Because this will have a unique solution. Using this reduced. Yes, what is the question?
No, I said thanks. Thanks for the clarification.
Oh, okay, fine. So this, we know this matrix has determinant 6. So when we do convert it to reduced row echelon form, I should get identity. So one more thing before this is that every matrix can be converted into row echelon form or reduced row echelon form, right? And how do we do that?
Elementary row operation.
Yeah, the 3 row
Gaussian
operations that we discussed. The elementary row operations. So what do we do here first?
R2 minus 2R1. R2 minus 2R1.
Yeah, I want to make this entry 0 because this is my pivot here. And the pivot is already 1. So no problem, right? So R2 is R2 minus 2R1. 1, 2, 3. 2 minus 2. 1 minus 4. 0 minus 6. The third row as it is. Is it in row echelon form?
No.
No. For one reason, this is not 1, right? So let's make that 1. R2, I'll multiply R2 by minus 1 by 2. So 1, 2, 3, 0, 1, 2, 0, 1, 0. Is this in row echelon form?
No, not
because
yet.
this entry is, yeah. So R3 is R3 minus R2. I want to make this entry 0. Why am I not using R1 here? Instead of R2, why am I not using R1?
Because of pivot
It has
entry
all
here.
the entries there.
Because
It has
other
an
entries will
entry
become
here.
non-zero.
I'll be disturbing the 0 entries. So 1, 2, 3, 0, 1, 2, 0, 0, minus 2. Is this in row echelon form?
No, we can
Not yet.
like divide last row
To
by
divide by minus 2.
minus 2.
The pivot is not 1 here. 0, 0, 1. Now this is in row echelon form. But this is not in row reduced row echelon. So when you do that, you do two more steps. You make these two 0 and then this 0. Then you will get the identity matrix, right?
Yes.
Because the original matrix is invertible, the reduced row echelon form is always going to be the identity matrix.
It will always be an identity matrix. I mean, if there is no non-zero row.
Original matrix is invertible. Yeah. Okay, then why are we doing all this? Yes.
Yeah, if the original matrix is invertible, is it not sufficient to just find the determinant of it?
Yeah, but why we are doing all this is because we can, that's what I was asking next. So the solutions of Ax is equal to B and Rx is equal to B are same, right?
Yes.
Yeah.
Yes.
Not B, it will be some C after doing. So if the original matrix is invertible, I can just find the determinant, that is fine. But solving that system may not be that easy. But when I convert it to this system, if the matrix is invertible, I directly get the solution, right?
Yes.
The final matrix Rx equals to C. Why not? I mean, because
it's not B because I would have done some row operations and that B would have changed to some other vector, right?
okay. Is this a notation to give to some final matrix when we do this reduced echelon form after that? Rx
No. See here, why I wrote R is because if it's reduced row echelon form or even row echelon form, but reduced row echelon form, you will directly get the solution.
And
C is whatever is that vector you get. Yeah.
But while we are reducing any matrix to reduce row echelon form or row echelon form, you can even find the solution for a non-invertible matrix also, no? Right? So then why?
Yeah.
Then why are we bringing that topic
No.
into consideration every time that?
The invertible thing, is it?
Right. Because this operation.
No, I was telling if the matrix is invertible, my reduced row echelon form is directly going to give the solution.
But even matrix is invertible, like it is not invertible, then also I will get the solution.
Yeah, you will get the solution. No, I just mentioned that if the matrix is invertible, I'll get identity matrix. That's all. It has nothing to do with
I
this
thought there is some relation or what? No, I thought there is some relation.
No.
Okay, thank you.
Okay, so how am I going to find the solutions if I have Ax is equal to B, that Gaussian elimination?
You do the augmented matrix.
Yeah, the augmented matrix.
One question, apart from like any matrix being invertible, is there any condition that where like we cannot derive this ray echelon form of any of the matrix?
No, for any matrix you can arrive at row echelon. Okay. For any matrix, irrespective of whether it is square, rectangular, it doesn't matter. For any matrix you can find the row echelon form, reduced row echelon. So you do row operations to the augmented matrix and then you converted it into either row echelon form or reduced row echelon form and then find the solutions for this system, and whatever solutions you get here will be the same as the solutions that you wanted for the original system, right?
Yes.
And while doing this, trying to do this, that is where you use the elementary row operations. So when you interchange two rows, what you're actually doing is you're just interchanging the equations, right? So suppose okay, let's take this. x1 plus x2 is 1. x1 minus x2 is 0. Suppose I have this system. A x is equal to b. So now suppose I take the augmented matrix. 1 minus 1 plus 0. I take the augmented matrix and I interchange two rows. What I'm actually doing is I'm just writing this equation first and this equation next, right?
Yes.
1 minus 1.
Oh, yeah. So, but if I interchange two columns, what happens?
Then you are actually
Determinant becomes negative.
The variable gets interchanged.
Yeah. When I interchange two columns, 1, 1, minus 1, 1. And if I had interchanged these two columns, this is my first column, this is my second column. Here I have interchanged the two columns. So now what is my system? 1 minus 1, 1. x1, x2 is equal to 1, 0. So this is x1 plus x2 is equal to 1 minus x1 plus x2 is equal to 0. Oh, here it doesn't make a difference because it's a symmetric matrix, I guess.
Yeah, it's not changed.
No, it still makes a difference, right? Huh?
Yeah, we'll change the column.
The original matrix was symmetric, so it didn't make a difference. Let's say I put 2 here. So if I had this 2, then this would be minus 1, this is 2. So now I'm completely changing the solutions, right? What is the solution here? 2x is equal, x1 is equal to x2. So x1 is equal to 1 by 3. x2 is equal to 1 by 6. Is it? No. Oh,
2 by 3.
Now what is the solution to this system? 1, 1, minus 1, 2. What is it? I just found the solution to this system here. What is the solution to this system?
x2 is becoming 1 by 3 now. x2 is becoming 1 by 3. x2 1 by 3. And then x1 is becoming 2 by 3. And just reverse. x2 is 2 by 3 and x1 is 1 by 3.
Yeah.
So the solution itself changes, right? Like I'm changing the system itself. So this is not allowed. Interchanging columns is not allowed. Only row operations are allowed. Fine, you can interchange two rows.
Now x2 is 2 by 3 and x1 is 1 by 3. In the final solution, after column operation, x2 is 2 by 3, x1 is 1 by 3.
No,
To the extreme right, ma'am. To the extreme right, whatever you have written at the bottom of your page. Yeah, it is x2 equal to 2 by 3. Sorry. Yes, it is interchange. It is interchange. Yes, interchange. Sorry, yes. Correct. Sorry. Correct, yes. Sorry. I'm extremely sorry.
No problem at all. Yeah, so you're allowed to do only row operations. And this is the reason why you're allowed to do only row operations. You don't want to disturb the coefficients of the variables. But you're allowed to change the order of the equations in which they appear. So that is why you're allowed to do only row operations. So you can interchange two rows. You can multiply a row with a scalar and add it to another row. And you can multiply a row by a scalar. When you multiply a row by a scalar, you're just multiplying one entire equation by a scalar, right?
Yes.
So suppose I do C times the first row, it's going to be this. This is not going to affect my solution, right? Because I can.
Yeah. Hello.
You are host Manan. Now you take the session.
Ma'am is not audible. Lost connection.
Am I audible?
Yes, ma'am.
I got I'm not confused. Just give me 1 second.
Voice is very low, I think.
Is it?
No, no.
No, I was talking to myself, so.
Okay.
Yeah, so we were discussing that the solutions of Ax is equal to B and the solutions of the reduced system Rx is equal to C. So you take the
Ma'am, your
augmented.
screen is not visible.
I still haven't shared. I am not co-host, so I don't have the option to share. So yeah, till they make me co-host, we'll just recall what we did. So yes, you take the augmented system A, B, and then you reduce that system to R, C.
And we will never do the column. What is that?
Column operations.
Yeah, column operation. We'll never do.
No, we are not allowed to do column operations because for this reason. No, I told you, no, when you do column operations.
No, ma'am, not in this. Otherwise, also we will not do the column
to
operation.
find determinant and all, you can do column operations. That is not the problem.
No, I'm talking about the few further classes when we are doing. So we'll be doing the column operations, no, ma'am. There.
No, if you want to solve a system of linear equations, you're not allowed to do column operations.
Okay. For the system of linear equations, we'll not.
Yeah. Okay. If you want to do column operations, what you can do is take, so what you have Ax is equal to B. Take the transpose. X transpose A transpose is equal to B transpose and do column operations here. But that's not what we have studied. So you
that will be simply complex.
Yeah. Okay, so CP, I guess, was asking when did the session start? It started at 9:30. Yeah. Okay, so fine. We are still to discuss independent and dependent variables. When do you say a variable is independent and dependent?
And can you give an example of finding inverse to reduce the row operation?
Example of what? Can you please repeat?
Find out the inverse of a matrix via reduce row operation. We put that in identity matrix, right? And then.
Yeah. Okay, we'll do an example. Okay. Before that, when do you say a variable is independent?
If in a reduced echelon,
When the determinant
it doesn't have a pivot in it.
So after you reduce it to what? In the reduced echelon form, RREF. After you do RREF, if there is any column without a pivot, the variable corresponding to that is an independent variable, right?
Yeah.
Can you repeat?
Yeah. Variables corresponding to columns without pivots are independent variables and dependent if they correspond to pivots. So say 1, 2, 3.
Is it referring to a row without a pivot?
No, it's a column because my first column corresponds to my first variable, right? The first column is the coefficients of the first variable, right?
Yes.
Columns? Just okay. Go ahead on the example, then we can come back on.
Here, I have this system, right? The coefficients of x1 will be in my first column, right?
Right.
So the first column corresponds to x1, the second column corresponds to x2.
Now you're referring a pivot, a column without a pivot.
Yeah, I'll do that.
Yeah.
So what was it? 0, 1, 1. This was 0. This is in reduced row echelon form, right?
Yes.
Yes, ma'am.
There is a pivot here. There is a pivot here. Now you look at the columns. Does this column have a pivot?
Yes.
Yes.
So x1 is a dependent variable.
Correct.
This column has a pivot. x2 is a dependent variable. The third column, which corresponds to x3, does not have a pivot. So x3 is independent.
What have you written above, ma'am?
But the pivot itself is taken reference to the row only, ma'am.
Yeah, you take pivots for the rows, means you take the leading non-zero entry of each row, and then you consider column wise. So the first column.
Let's get back to the statement. It is not taking reference to row at all. That's why I was confused.
That's because I'm trying to refer to the variables. No, I am seeing what is happening to the variables. So my first column tells me information about x1.
And I'm clear until the last phrase, columns without pivots, with pivots. So that's what I was a bit confused. The pivot should be taking reference to row.
I think that definition, ma'am, need to be reviewed. Variables corresponding to columns with pivots. So independent variable means there should not be any pivot element, right?
Yes. Oh.
Yeah.
Variables without pivots. Okay.
Yes. Yes.
Yeah.
Sorry.
Thank you, ma'am.
Is this clear? Is it clear now?
Yes. That is typo error.
But still, I miss a link there. It is not at all referring to a row without pivot.
Yeah, that's because when I consider rows, no, I'm not talking about the variables. I'm talking about the equations, right? When I take a row, I'm talking about one entire equation, right?
Yes. You are talking about
when
all
I take
three
a column,
variables.
if I take a column, if I take the first column, I'm talking only about the first variable, x1.
Yeah, that's right.
Yeah. So when I want to know about x1, I will look at the first column.
Okay.
If there is a pivot, that is the only element in the column, right?
That's a dependent, okay.
So if I have this system, okay, not this one. Okay, say suppose I have.
Is it that simple to tell that a variable without a pivot row is an independent variable?
Yes, it is. So suppose I have this system, say 0, 1, 0.
Right.
When I have a 0 here, I want a 0 here, right? Because if this is not 0, then the system does not even have a solution, right?
Correct.
Yeah. So let's take this now. Now,
ma'am,
what is this?
If my third column is entirely 0, then also x3 is dependent variable, right? Then also x3 is independent. Right?
Yeah. So now what is this system? x1 plus 3x3 is equal to 0. x2 plus x3 is equal to 1. 0 is equal to 0, right?
Yes. This is my 0 x3 is equal to 0, no ma'am? Yeah, 0 x1 0 x2.
Yeah, 0 x1 plus 0 x2 plus 0 x3 is equal to 0. So this is not going to give me any information. Now, from here, I can write x1 is equal to minus 3x3. x2 is equal to 1 minus x3, right?
Yes.
x3 can be anything. But once x3 is fixed, x1 and x2 are fixed. Right? x1 and x2 are dependent on x3. Right? Yeah. So columns with pivots, the variables corresponding to columns with pivots are dependent. without pivots are independent.
Yes.
Okay. So we wanted to do an example where we find the inverse using the Gaussian values. So what was it? 2, 0, 1, 0, 1, 0. We already know the inverse of this matrix, right? We calculated some time back.
Yes.
We'll see if we get this. So if I want to find the inverse,
Further, do we have to go through the same, find the adjugate of A, then go for...
No, this is using row operations. We are not going to do using that formula.
No, I'm talking about the inverse.
Using row operations, we are going to find the inverse.
How to get the inverse with row operations?
Yeah, I'll tell you. So you take the matrix A here, and then you take the identity matrix. Okay. So 3 cross 3 identity.
Ma'am, what you are explaining now?
I'm trying to find A inverse using row operations. Instead of doing A inverse is equal to 1 by determinant of A into adjoint of A, I'm going to use a different procedure to find the inverse. That's all.
Actually, on the right hand side will be A inverse.
After doing the row of reduced echelon form, you will find A. Yeah.
Yes.
Left hand side will become identity matrix. Yeah. So now you try to make this in the reduced row echelon form. So because the matrix is invertible, the reduced row echelon form is going to be identity matrix, right?
Yes.
Yeah. So let's do that. So this is 1, 2, 3, 1, 0, 0, 2 minus 2, 0 minus 4, 1 minus 6, 0 minus 2, 1 minus 0, 0 minus. Last row as it is, right?
Yes, please.
And then I want to make this entry 1. 2, 3, 1, 0, 0, 0, 1, 5 by 4, 1 by 2,
minus 1.
minus
Can we
1
switch
by
the rows
Minus
R2
1
to
by
R3?
4.
What is it?
Switch rows, interchange
Yeah.
R2 R3.
Will that make it easier?
Yeah.
No, we've already proceeded, ma'am. So please proceed.
Okay, fine.
And while calculating inverse with this method as well, before that we have to always calculate the determinant, huh? To check whether
No,
it's
you don't
non-zero.
need anything. You don't need the determinant. You will directly get. To know it is non-zero, yes. See, even if you start with this, if this matrix is not invertible, your reduced row echelon form won't be the identity matrix. So there also you will know that, that it is not invertible. And then I want to make this entry 0.
Come again, I didn't understand. What did you say? What was that? Why determinant we need to check before we start this?
No, by this procedure, I will directly get the inverse. I don't need the determinant of the matrix. Means there is no formula that I have to apply. I will directly get the A inverse.
Okay. Method is this procedure.
So this is using row operations. We are finding inverse. That's it.
Okay.
Sir has done a problem on this or not?
I think we have done it, ma'am.
Yes, ma'am. Yes, ma'am. No, ma'am. In the lectures,
He has shown
not.
it, ma'am. He has shown
Yes,
it
ma'am.
in the lecture.
Yes,
He has
it's
shown
not
it in the
there.
lecture.
It is not there in the lectures, ma'am.
Just done.
No, I think it is there. Yeah.
It is not there.
It is in the lectures as well, if I'm not wrong.
Which
It is there in the
lecture?
lecture.
It is not there in the lectures. I checked it out. It's not in the lectures.
It is
Okay, if it is
I
there,
have done it, so it must be in the lecture. Otherwise,
It is there in the lecture.
It is there in the lecture.
It is there in the
I have
lecture.
seen it.
okay.
It's not there.
Even if it is not there, this is something new that you are learning. If it is
Yes,
not
ma'am.
there, you can ignore it for the exam point of view. Yeah. So this is, I want to make this 0. So this minus this 1 minus 1 minus 12 by 4 minus half 1 by 4 1. And then I want to make this entry 1. So I'll multiply the third row with minus 4 by 5. Minus 4 by 5. So
2 by 5.
Okay. Minus 1 by 5. Minus 4. Okay. Now I want to make this entry and this entry 0. So that is R2 is R2 minus
4 by
5 by 4 R3.
4 by 4.
Or 4 by 4. Okay. And R1 is R1 minus 3 R. So 1, 2, 0.
5 by 4 R3.
No, R1. I am doing first row. This one. So this becomes 0.
Yes, ma'am.
So 1 minus 6 by 5. Are we doing something wrong? Because I don't think we'll have by 5.
No, it's correct, ma'am.
Okay, is
Ma'am,
it
we are doing
correct?
R1 minus 3 times R3, right?
Yeah, yeah. 1 minus 6 by 5.
6 by 5. Minus 1 by
Minus 1 by 5. 0 minus 3 by 5.
3
Plus 3.
3 by 5.
4 by 5. Or no, 12 by 5.
12 by 5.
And then R2. 0, 0, 1. 5 by 4. It should be 5 by 4, right? 5 by 4 minus 5 by 4. So I'll get 0.
Yeah.
1 by 2.
No, ma'am, we'll directly add R3. No?
1 by 2. 1 by 2 minus 1 by 2.
We will directly add R3. R3 with. I want to make this entry 0, no?
This has become 1. Sorry. I'm looking at that. Okay.
Oh.
Yes. This also becomes 0 now.
What? This becomes 0, is it?
I think yes, ma'am. I guess so. 1 half minus 4, 5 fourths of 2 by 5. It is.
Okay.
Yes, it becomes 0.
Then minus 1 by 4 plus 1 by 4. 0 again, okay. And then 0.
Minus 1, I guess.
Plus 1, is it?
Yeah, sorry, plus 1, yes.
And then
Third row is same.
third row as it is. I think we are doing something wrong somewhere, or the inverse previously was wrong, or the matrix that is
2 also we need to make it 0.
I
What is
think
the
the
determinant
original
of this
matrix was
matrix?
different.
Oh, yeah. Okay, fine. Yeah. It was 1, 0. Now it's 0. I wrote it 0, 1. Okay. Now I want to make this entry 0 because I want to make this part identity, right?
Yes.
So I will do that by doing R1 is R1 minus 2R. 1, 0, 0. Minus
1 by 5. Minus 1 by 5.
3 by 5. 12 by 5 minus 2.
2 by 5.
2 by
2 by
5.
5.
0, 1, 0, 0, 0, 1, 0, 0, 1, 2 by 5 minus 1 by 5 minus 1. So this is my A.
So you're in this method, the matrix you start with, it has to become an identity matrix through row operations.
If it is invertible, only then it will become identity matrix. No, otherwise it won't become identity. No.
Okay, I mean, assuming that it's inverse, so you will do the row operations to get identity, so that the one which was earlier identity will become the inverse.
Yeah.
But ma'am, here But this is one thing here is we need to start up like when a matrix is given, how do we know that it's inverted, right? We perform all these and finally, it's like a priori you need to know, yes, it is an inverse matrix. Right?
Yeah. So it's always better to first find the determinant. Because why will you find inverse if it's not even invertible?
So if the determinant is not zero, then there's a chances that it is an invertible matrix. Right?
If the determinant is not zero, by this procedure, you will end up with the inverse.
But this is for all the matrices be the case?
Yeah, this is for any n cross n matrix which is invertible.
Okay.
So it will be a square matrix, no?
Yes, for a square matrix.
Yes. Square matrices.
The other one is the usual adjugate, no?
Yeah. That is find the cofactor matrix, find the transpose and all that.
Yeah.
Earlier method.
Yes.
Ma'am has discussed CP.
Huh?
I think that has been discussed. That's what I told you.
Yeah, that has been discussed. Yeah. Okay, so shall we start vector spaces?
Yes, ma'am. Ma'am, here this Ax equal to B, right? This is true for all matrix, whether it is a square matrix or a rectangular matrix, right?
No, while Ax is equal to B.
While solving the system of linear equations,
this is for any.
That is true for all, you know.
Yeah. Okay. Oh, we did not discuss this, no? Solutions when it has infinitely many solutions.
No, it's only for square matrix because we can't talk of identity matrix for non-square matrix.
No. He wasn't asking about this. In general, Ax is equal to B.
But he was also, I think, he was mentioning, right? Like if for all the matrix, whether it is square or not.
CP, we can solve system of linear equation whether the coefficient matrix is rectangular matrix or a square matrix. We can solve that.
Okay.
Yeah. We can solve that, no? Right, ma'am?
Okay. Yes. Irrespective of how many variables and how many equations you have, you can always solve Ax is equal to B by doing the row echelon.
Correct. Yes,
okay. What can you tell about the number of solutions to Ax is equal to B?
If the A matrix is invertible, non-zero, then there's a unique solution.
Yeah. Oh, okay. I think this and all will come when we talk about dependence, linear independence and all that, right?
Yes.
Yeah.
Okay, fine. Then we'll discuss that. Anyway, you know the rank of a matrix and all that. So doing it there is better. Okay. So shall we start vector spaces?
Ma'am, could you repeat that rank of the matrix?
Solution.
No, I haven't discussed rank yet.
That will come down.
Only dependency and independent variable we have discussed, no, ma'am?
Yes.
Yeah. So whenever you have a yes, what is it?
I mean the three solutions, unique and infinite solutions.
So we'll discuss that. Is it coming in week 2?
Yes.
Week 2 there is a solution part.
Yes, ma'am.
Yes, there is a.
Oh, okay, fine. So in week 2, when can you say it has infinitely many solutions and all that? In terms of independent and dependent variables, right? Fine. Okay. So Ax is equal to B has infinitely many solutions when
there is a non-zero root.
When determinant is 0.
No, determinant you can talk only for square matrices. No, but here the system may be rectangular also.
So she's talking about number of variables and number of rows, but I'm confused actually in that.
When there is an independent variables, yes.
What are you confused about when there
are? Like that equation when the number of variables is lesser than number of rows and
variable is
some
greater than variable is greater than number of
some relation. I always forget that.
Since you are discussing here this one infinitely, so can we sort of assume that if the number of independent variables is more than the number of equations, then it is likely that there will be infinite variables?
No, not independent variables. When there are Variables, when the number of variables.
No, that's what
yes.
I'm saying. Total, there will be total number of, let's say there are totally in m by n matrix. Okay. So if it is an m by n matrix, we can say that the number of equations are m and number of variables are n. Okay. And n is greater than m. Then can we blindly immediately assume that this system of linear equations will have infinite solutions? Because if we go to the row echelon form, obviously there will be non-pivot columns, which will be there, right?
Yeah. So when this happens, when n is greater than m, that is you have
more variables.
Yeah, two rows, two equations, and say 3 variables. What happens is that it's an underdetermined system, right? You need at least 3 equations to find out 3 variables, right?
Yes. That is for unique
solution,
right?
So it's underdetermined, means you don't have enough information about the variables, so there will definitely be infinitely many
that's
solutions.
Right. So this is correct, right? N greater than n is infinite.
Yes.
Yes, thank you.
And when m is greater than n, you cannot really tell in this case because the number of equations, the equations may repeat also, right? There may be redundancy, like x1 plus x2 is equal to 1, x1 minus.
More likely it will be inconsistent.
It is only additional information.
Additional information, but in this case you have 2 possibilities, right?
Yeah.
There can be unique solution or no solution. No, not infinite. See, in this case, these 2 equations are actually the same, right?
Or we can say it's inconsistent, no system.
So
yeah, basically, ma'am, if it is like a linear combination, then it will be like unique solution. But in case of if it is totally different, then no solution, right? Because x1's value may be different in both of them.
Yeah. So you take this equation.
Right?
No, not infinitely many solutions. Here you have enough number of equations to determine the variables. No, so in this case you will not have infinitely.
Variable independent, right?
And we can also check by if a1 by a2 is equals to b1 by b2 is equals to c1 by c2. Then
okay, I agree that here you will have infinitely also if all the 3 equations are going to give you the same equation. Like this. Yes, 1 second, I'll finish this. So in this case you have more equations, but still the data is not enough, right?
Yeah. Yes.
Okay.
Yeah. So I agree, all 3 can occur. Yeah. So what was someone was asking about something? What is?
We can also check this infinite and unique solution by if a1 by a2 is equals to c1, b1 by b2 is equals to c1 by c2, then we see that we have infinite solutions, and if a1 by a2 is not equal to b1 by b2, then we say
So
unique solution.
those are actually giving a geometrical meaning. Means their slopes are the same, means they are parallel lines and all that.
For the example that you have taken here, just beside, yes, actually, they are not same equations. Actually, it's not a different equation. If we maybe have different ones, because if you take 3 common from second and 2 common, the 3 equations become the same, right?
Yeah, that's what I'm telling you. Here I have 3 equations and 2 variables, but ultimately they are just one. This is just one equation, right?
It's just like you are multiplying both sides by same value.
Yeah. So in this case, you will have infinitely many solutions. Suppose I put 0 here. In this case, I have no solution, right?
Yes.
Yeah.
Suppose I put, in this case, I'll have a unique solution, right? Just take these 2 systems and solve.
I think more chances of it being inconsistent rather than infinite.
No, it depends on the data.
Okay.
There is, it depends on the right handle. Okay, so basically if there are independent variables, then there are infinitely many solutions, right?
Yes, ma'am.
And if all the variables are dependent, then there is a unique solution, right?
Means there is the pivot column in every
When no
all
solution,
pivot element in every column.
No, in this case, you cannot tell there are no solutions, no, unless you get, okay, unless you get something like this, 0 is equal to some absurd quantity.
Okay, okay.
Yeah. So if you get the last row to be 0, but the last coordinate of the right-hand vector is not 0, then in that case, there will be no solution. But if the entire last row of the augmented matrix is 0, then it means that there are independent variables, in which case there will be infinitely many solutions. If there is a pivot in each column, then it means that it is a unique solution. Yeah.
So ma'am, in the unlikely event, we have one equation, like just now we are saying, you have the right side as some scalar value, non-zero, but all the others zero. That is inconsistent, right? I mean, like,
Yeah.
there is no solution. But if both sides are zero, then infinite, right?
This is inconsistent, right? This system is inconsistent. 1, 1, 3, 3, 1, 2, 2. So when I reduce this system, I'll get 1, 1, 1, 0, 0, some -2 or something, -2, 0, 0, 0. So this is inconsistent, right?
Yes, yes, ma'am. Yes.
Yeah. But if I had, say, some other number here, and then this is consistent, right? In this case, it's infinitely many solutions.
And even
no.
here,
In this case, there is a pivot in each column, so unique solution, right?
Yeah. Yes.
Yeah.
Unique solution.
Yeah.
Ma'am, what about the number of solution of homogeneous linear equation?
So when you have Ax is equal to 0, x is equal to 0 is always a solution, right?
It is unique.
So there is no, this is homogeneous system, right?
Yes.
Yeah.
So
So
it is
in this
unique
case,
or
you have either a unique solution or infinitely many solutions. In fact, the unique solution is the zero solution.
Zero.
This system can never be inconsistent because x is equal to 0 is always a solution.
everything.
And when in the other case, when you mentioned that this is okay, the matrix one is clear here because we have two pivot. There's another where one of the equations was like you have all zeros equal to 0. So that is infinite solution, right? So
if I had, say, 0 here, 0 here, in this case, I have infinitely many solutions, no?
This one.
In the first case, when n is greater than m, it has infinite many solutions. Could you please like show some example for that?
Yeah. So say I have more variables, right? So 1, 2, 3. And I have less equations. So say 0, 0, 1. So in this case, it's always going to be infinitely many solutions, right? There's one free variable always.
And there is
infinite many or inconsistent solution?
If this is 0, okay. If this happens, then it is inconsistent. Okay. Unique solution is not possible.
Yes.
Because you have more variables and less equations. So pivot per column is not possible.
This is also infinite, right? Not x2 and x3 are independent.
No. Here the last row, this is 0, this is 2, no? So no solution.
Yeah, okay.
If this was 0, then infinite, yes. Even if this was 1, it's still infinite because there's no pivot here. So x2 can be chosen in any way we want.
Ma'am, one query, like not related to this, but since you have taken this example, in this case, the second column's second row element is 0, right? And the third one is 1. So in this case, is it a row echelon form or it's not a row echelon form?
This is row echelon form. This is not reduced row echelon form.
Okay.
Now it's
Okay.
reduced row echelon.
Right. Okay. Fine. Thanks.
It doesn't matter what this entry is because this is not pivot, no?
Okay. Yeah. Thank you.
Okay. So shall we proceed?
Ma'am, when we have pivot in each column, then it's infinitely many solution.
No, pivot in each column means unique solution.
Unique solution.
If there is a pivot in each column, what do you get? Reduced row echelon form is this, right?
All are dependent.
Yes, ma'am.
Then you'll have some A, B, C. So my X is equal to A, Y is equal to B, Z is equal to C. Unique solution.
Just one question, like for final examination, what were the weightage for like first to fourth?
So you cannot tell a particular weightage because if I give you a problem from the 9th week, which involves solving a system of linear equations, where will you put it? Week 9 or week 2?
Okay. Okay.
Yeah,
Any
so
like
that is the reason why we cannot give a weightage, in fact, because everything uses concepts of the previous week. It's not like, it's
okay,
like
it isn't
I
combination.
always use addition, even though I've studied it in my first standard. It's like that. Yeah.
Ma'am,
here just before we
number of questions, I mean, if it will be there in the final exam. I mean,
I don't remember exactly, but it's some 12, 13,
12
or 15, I guess. Like you can expect 15. I don't remember exactly.
Oh.
Ma'am, coming back to this problem again, if it is not reduced to echelon form, it is just reduced echelon form, and I'm getting pivot in every column, still it will be a unique solution?
Yeah. You needn't do so much, no? A row echelon, reduced row echelon form. See, the advantage of doing reduced row echelon is that you directly get the solution. Here, if it's row echelon form, you have to do backward substitution.
I can always,
get
if
this.
it's a reduced echelon form and every column is having a pivot, then I can always convert it to reduced echelon form, right? Okay.
Yeah.
Fine. Yeah. Thanks.
So you see the advantage, right? There, you make these 0.
Yes, ma'am.
By making these zeros, you directly get
It
the
will be
solution.
very easy to, right.
Yeah. But then you are actually doing more operations to make these 0.
Right. Yeah. Thanks.
Staying with this matrix, so we can for this we can say the rank is 3, nullity is 0, dimension is also 3, right?
No, what is dimension?
Dimension is 3.
No, what is dimension? Dimension of a matrix means what?
Like let's say it is R3. We are taking R3 here. So for this R3, let's say we are this is representing some R3 space. So for that R3, there is a dimension will be 3, right? In this case, for the
R3 dimension is 3, but I don't understand how this is going to represent R3.
Okay.
Rank nullity is fine. Rank is
whenever we talk about
these three can be the basis vector, right? These 3 can be standard basis, right?
Okay. These 3 columns will form a basis vector for R3. Yes.
But ma'am, for a matrix, rank is the dimension of the matrix itself, right?
No, what is dimension of the matrix?
That is rank.
Okay, maybe it's a different name, but you stick to rank because that is better.
Ma'am, can you just show me that when you were explaining the row echelon form?
Okay.
Yes, ma'am. Here, stop, ma'am. Go down. Go down. Come to row reduce, row echelon, row reduce.
This is row reduce.
Yeah, last line you can show. We came to some conclusion where we cannot reduce anymore, and some numbers were still there in column pivot. One pivot was not there, like that was there, na? So you were telling.
Yeah.
And I think she is referring when third row had become 0 and
Yeah. Here, ma'am. Yeah.
Yes.
This case we will have indefinitely many or
infinitely
dependent
many
and
solutions.
one independent variable will be there, no?
Yeah. So infinitely many solutions.
Okay, ma'am. Okay, ma'am. That is.
Yeah.
Then move to next video.
Next, what next?
Next week or next concept.
Okay. Okay. So we'll begin vector spaces. Do you remember the definition of a vector space?
Some conditions like closure under addition, closure under multiplication.
So V is said to be a vector space. It always comes with two operations, plus comma dot, where this plus refers to addition and dot refers to scalar multiplication. Okay. So this is said to be a vector space if firstly plus and dot are both closed with respect, means they are closed. Plus is it acts on two vectors. You add two vectors and the output is a vector. This is plus. Okay, this is what plus does. What dot does is you take a scalar and then you multiply it with a vector. The output should be a vector, right? So if I have v1 comma v2 in v, then v1 plus v2 should be in v.
So
Is
when do
someone
we say
talking to me?
V is equals to R3.
define
Can you please mute if you're not talking to me?
you define again the word?
What is it?
You said closed, right? How do we?
It's closed in the sense when you add two vectors and you do this operation on two vector, means you take two vectors in the space and do this operation, the output is also going to be in the same space. So everything lies within the same space. Yeah. Fine?
Yes.
That is what we mean by the closed under addition.
Yeah. And alpha times V should be in V. Alpha belongs to R, V belongs to V.
V can be R3, right? Vector space.
What is it? It can be any vector space. It can be R2, R3, anything.
Only these two are there. We have to check for zero vector also, or only these two?
No, see. No, I haven't even written down the conditions. I have just started.
Okay.
So along with this, you have 10 conditions. Or what? 8 conditions.
Closed under addition means that addition which we are doing, that resultant should also be in the vector space.
Same set, yes. Yeah. Right. So this is closed under scalar multiplication. When you do scalar multiplication, you are still in the vector space. Okay?
Yes.
And along with this, what are the conditions that addition should satisfy?
Zero vector, if I add zero vector, it should be the same vector.
Okay. So first is commutative property. That is V1 plus V2 should be equal to V2 plus V1.
Yeah.
And then associativity. It doesn't matter how you add three vectors. The order in which you add doesn't matter. And then
zero vector.
There exists a zero vector in V such that 0 plus V is V plus 0 for all V in V.
There's also
this is equal to V.
Inverse vector or like minus vector, negative vector, like whatever we call it.
There exists a W in V such that V plus W is equal to W plus V belongs is equal to 0. Yeah, the additive inverse.
It can be V prime also, right? Additive inverse.
I am just using W, V prime. Okay. So there is a vector like this. And then with respect to scalar multiplication, what are the conditions?
Alpha into V1 plus V2 equal to alpha V1 plus alpha V2 and 1 into V equal to V of course. And
alpha v1 plus v2 is alpha v1 plus alpha v2.
And alpha v1 plus beta v2 equal to alpha plus beta equal into v1.
Alpha v plus beta v, and then
alpha into beta.
Alpha beta v is alpha beta v. You can do the addition, scalar multiplication. This is distributive property of addition. And yeah.
Here we are not talking about multiplicative inverse, right?
No, there is no multiplication defined at all. It's only addition and scalar multiplication. There is no multiplication. There is no concept of multiplication.
Multiplicative inverse, we are not talking here, right?
One is
so there is no multiplication at all.
Okay.
Scalar multiplication.
So there is no multiplication at all. So there is no multiplicative inverse. Okay. So a set along with these two operations, plus and dot, plus is addition, dot is scalar multiplication, satisfying all these conditions is said to be a vector space. Fine?
Yes.
And we have seen a lot of examples. You can also go back and watch the revision session that happened for quiz 2. The first revision session in which I discussed vector spaces. It's discussed in more detail and examples and all that.
Quiz 1 revision session.
Huh?
Quiz 1 revision session.
Quiz 2 revision session. I think it was 5th March.
Where's the link for that one? Same YouTube link, is it, or?
Yeah, you will find everything in that supplementary contents. See.
Okay.
Yeah. So in supplementary contents, go for this.
Okay.
Yeah. Okay. And then when do you say a subset of a vector space is a subspace?
If it is closed under
three conditions.
Yeah.
And it
is a subspace if 0 belongs to W firstly, right? The zero vector of the vector space belongs to W. W1 plus W2 belongs to W.
W, yeah.
If W1 comma W2 belongs to W. Okay, for all W1, W2 belongs to W. It's closed under addition. And it is closed under scalar multiplication.
Here 0 means like if it is R3, then like 0,
0, 0, 0. Yes. This is the notation for the 0 vector. It need not be the number 0.
It is not always that it will be 0, 0, 0.
Yeah, it depends on the vector space, what the 0 vector is. Fine?
Yeah.
Okay. So these are the conditions you need to check for whether a subset of some vector space is a subspace. So why this is nice is because if you know some vector space, say R3, and we are talking about a subspace of it, instead of checking whether this is a vector space by checking all the conditions, it's enough if you just check these 3 conditions, right?
Yes.
So if you can identify a big vector space for which this is a subset, then checking these 3 conditions will be enough. Okay, so we had seen that lines.
Ma'am, to check a vector space, do we need to check all these 8 conditions, or just we need to check those 2 properties, closed under addition and
8 plus 2,
okay.
10. These 2 first, and then these 8.
Okay, ma'am.
Ma'am?
Yeah.
If I try to recall in one of the sessions, I think it was discussed that first of all we have to check closure under addition, closure under multiplication. If it fails, then we need not to proceed for remaining it, right?
Yeah. If any one of the 10 conditions fails, done. It's not a vector space. Only if all the 10 are satisfied, it is a vector space.
So first we need to check those 2 and then can check the properties that is not satisfying, then we can directly say it is not a vector. Okay.
What is it? Can you please repeat?
I'm saying that to disprove any vector space, if it is not a vector space, we can check a property. If it is not satisfying that vector space, then we can say it is not.
Yes. Okay. So yes, what is linear combination of certain vectors?
Just scalar multiples.
Yeah. Say v1, v2, vn. A linear combination is nothing but something like this. Alpha I Vi, summation alpha I Vi. I is equal to 1 to n.
The screen is not visible.
No, screen is not.
Is it?
It is visible for us.
Your
And
screen is
visible, but
frozen.
what you're writing we cannot see.
Upside screen is visible.
Screen is frozen.
Now it's not visible.
Yeah. What about now? Is it visible?
No, ma'am. Not at all.
Just coming up.
Just
Oh.
says you have shared your screen. That's all, but nothing is coming.
Nothing?
No.
We're just seeing that you have shared you started screen sharing, but nothing is coming.
That message is appearing on this.
It's saying Sushmita P has started screen sharing.
Now is it showing I am not sharing?
Yes.
So now you're not
Okay.
seeing.
Let me try. Now?
Same message. Same message.
Okay, I'll probably log out and log in.
Okay.
Can you hear me?
Yes, ma'am.
Okay, I am not a co-host. Okay, so what were we discussing? We wait for them to make me co-host.
Ma'am,
We were
linear combinations.
So we were discussing about linear combinations. And when do you say a set of vectors is linearly dependent?
Linearly dependent.
Yeah.
If it is one vector with a scalar multiple of one linear combination.
It's a linear combination of the other vectors in the set. Yeah. So not necessarily scalar multiple of another vector. It can be 2, 3 vectors put together, a combination.
And your screen is not visible.
No, I haven't shared yet. I
When
was
one
just
vector is dependent on another, we can see it is a linear combination of some vectors.
Now is my screen visible?
Yes.
Yes, ma'am.
Okay. So yeah, we were discussing linear combination, and then what is linear dependence? When do you say a set of vectors is linearly dependent? So when some vector is a linear combination of the other vectors, right?
Yes.
Alpha n, Vn. But in this sum, you won't have the ith term, means Vi won't be there. Okay. It's just that when one of the vectors in the set can be written as a linear combination of some other vectors from the set. Or in another sense, what you can tell is alpha 1 b1 plus alpha n bn is equal to 0,
Or
where
not
not all
alphas are 0. At least one will not be
alpha.
0.
Yeah. So at least one of the alpha i's is not 0. Then you say that the set is linearly dependent. And when do you say it's linearly independent?
All will be surely 0.
When all the
And all the AIs are alpha are 0.
Yeah. So when you write the linear combination, means you put the linear combination equal to 0. This implies all alpha i's are 0.
0.
You cannot write it as 0, cannot be written as a linear combination of these vectors where the coefficients are non-zero, right?
Yeah.
This is a linear combination of 0, right? If I can write 0 is equal to this.
Yes, 0.
Yeah. So what is the relationship between linear dependence, linear independence, and solutions of Ax is equal to 0?
If it is linearly independent, then it is a unique solution.
Yeah. If columns of A are linearly independent, then
Means they are without the pivot column.
no, columns of A are linearly independent means you will get a pivot, no, everywhere.
Yes.
Yeah. In this case, I'll have unique solution. And what is the unique solution?
0.
Yeah. And if the columns of A are linearly dependent, what happens?
Infinite solution.
There will be infinitely many solutions. Because if they are linearly dependent, I am going to have independent variables, right?
Yes.
If they are linearly dependent, I will definitely have a 0 row, because of which I will have okay, not 0 row necessarily. There will be at least one column without pivot. That is why you will have, means linear dependence means that there will be at least one column which does not have a pivot, because of which there will be an independent variable, and hence there will be infinitely many solutions. If I have Ax is equal to 0 and A is a square matrix, then how can I check whether it is linearly independent? The columns are linearly independent.
Determinant.
Determinant is not 0.
Determinant of A is 0 means columns are
Linearly dependent.
Determinant of A is not 0 means columns are independent. So if you are given a set,
Regarding that pivot, what you were saying that if in their column, if it is a pivot, yeah. If there is
so if every column has a pivot, then there is a unique solution, right?
And that is linearly independent, right? I mean, those.
That happens when the columns are linearly independent. When the columns are linearly independent, then every column will have a pivot, and because of that, there will be a unique solution.
And if there is no pivot, then they are dependent. I mean, if any column.
If there is at least one column without a pivot, that will happen if the columns are linearly dependent. In that case, you will have infinitely many solutions. If there is one column without a pivot, it means that variable is independent, right? Means that particular variable is independent, right?
Okay.
So say 1 0 1 2 1 0 0 0. So in this case, it's 0 0 0. Okay. So in this case,
Next two are
this column doesn't have a pivot. So x3 is independent, right?
finite many solutions.
So you will have infinitely many solutions. Fine?
Yes.
Okay. And so if you have a set of, if you have a set and you are asked whether the set is linearly dependent or not. Suppose you have 3 vectors in R3. In that case, you can use this result, right?
Yes.
Write the three vectors as columns of a matrix and then find the determinant of that matrix. If you're given two vectors in R3, can you do this procedure?
No.
No.
No, because in that case, the determinant doesn't make sense.
Ma'am, here so for 3 by 3, when we are representing the columns, we have three vectors given. So we are writing as columns, and then determinant we are finding it out. And if the determinant is 0, columns are dependent, right?
Yeah, which means the vectors are
Sorry,
dependent.
vectors are vectors are dependent. The other cases, the columns will, the vectors will be independent.
Yes.
Ma'am?
But that's anyway homogeneous equations. That will be.
If I write those three vectors in terms of rows, so will there be any difference?
No, there won't be a difference because determinant of A and determinant of A transpose are the same. No?
Same. Right.
Why we are writing it as AX is equal to 0 is because if I
homogeneous, right? No?
if I have a system, if I have a set of vectors, say 3 vectors, if I want to find out whether they are independent or dependent, what I do is I do this, right? Alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 is equal to 0, right?
Yes.
So V1, V2, V3, suppose they are in R3, then I will get 3 equations, right? For each component, I'll get one equation, right?
Yes.
Yes,
Alpha 1.
Yes.
So that I want to find out whether alpha 1, alpha 2, alpha 3 are 0. If all 3 are 0, then
independent.
It is a linearly independent set. Yes. So when I write it as a matrix, it will be like this. This is the homogeneous system I am trying to solve.
Yes.
That is why this concept works. I know for a homogeneous system, definitely there is a solution.
So
I just want to know whether there is a unique solution.
So we can expand as V1, V2 by putting down the components, right? Columns.
Yeah. So it will be like say 1, 2, 3,
yes,
2, 0, 1, something like that.
Yes.
Yeah. Okay. So what if I had 4 vectors in R3?
It is
one vector is a linear combination of
dependent.
So this is always dependent, right?
Always dependent.
Because you know the concept of a basis. I know the dimension of R3 is 3. So any set of vectors with more than 3 vectors is a dependency, right? Yeah. Okay. So what is span of a set of vectors?
It is the vector space.
No.
All multiples.
It is the set of all finite linear combinations. Of the vectors.
With the help of these vectors, we can write any linear combination.
You know what a linear combination is, right?
Yes.
Finite linear combination means that sum is finite. That's all. If you have an infinite set of vectors, even then you can take span. But we are dealing only with finite vectors. So this span of, okay, say if I have a set V1, V2, Vn, span of this set is nothing but the set of all linear combinations. Belongs to this set. I belongs to. This is span of this set, right? And do you agree that this is a vector space always?
Yes.
Yes.
So the span of a set is always a subspace. So, What is it?
What you think that span of vectors is always a vector space.
Yeah, it's always a subspace.
From here, V1, V2 span of instead of basis, why you put the whole V1 to Vn? It's Vn, right? Vn or one?
Yeah, Vn.
But why that is in the span? Span, you can put inside span the basis not to get a vector space, but we have put the whole vector.
No. You can talk about span of any set. No.
Okay. But here in this case, we are taking all the vectors and as a set, right?
Yeah. I'm not telling these are basis vectors or anything. Any random vectors, I can talk about their span.
Okay.
Yeah. So the span of a set is always a subspace. And what is a spanning set?
It is a set which spans the whole vector space.
Yeah. So you have a vector space. So here you start with a vector space. You find the set S such that span of S is V. So this is my spanning set, right?
Yes.
Yeah. Okay. So what is a minimal spanning set?
The minimum number of
Elements in
vectors
the
which
set.
will span the vector space.
Yes, minimum number of elements in the set, with the help of which we can span the vector space.
Yeah, if you remove one element from that set, it's not going to span anymore, right? So minimum, you need minimum these many elements to span the set, span the vector space. If you remove even one element from it, it's not going to span. That is a minimal spanning set. What is a maximal linearly independent set?
Could you show example from minimal and maximal?
Yeah, sure. What is a maximal linearly
If we add
independent
one
set?
more vector in that, it will become linearly dependent set.
Yeah. So that is a maximal linearly independent set. And a basis is a minimal spanning set or a maximal linearly independent. Right?
Yes.
In fact, it is both. If it is one, it is the other. Okay, so what the question was, what is a minimal spanning set? Okay, so let's take R3. Let's take the subspace set of all x comma y comma z.
Yeah.
Such that x plus y is equal to 0. What is this?
How long it will take?
Subspace.
Are you talking to me? Are you asking me how long will it take? Okay. What is this?
Subspace.
Of dimension?
2.
What is the dimension?
3.
2.
No. It's not 3.
2.
It's 3.
Why is it 2?
2, ma'am. 2.
Because z is independent and the value of x depends on y.
Yeah.
One of these two is independent and z is independent.
Z is also
right?
independent.
Yeah.
Yes.
Okay. So can you give me a spanning set for this? Spanning set. I'm not asking for a basis.
Ma'am, what was that? Z is independent and out of x and y, 1 is independent, right?
Can you repeat this?
I can write it as x comma minus x comma z, right?
Right.
So I have two independent variables, no? X and z.
Right.
Independent variables means what? I'm allowed to choose x and z however I want.
Right. So dimension is 2.
Yeah.
You
give me a spanning set for this, not a basis. I'm just asking for a spanning set.
1 minus 1, 1 and 1 minus 1, 0.
1 minus 1,
1.
1. Okay.
1 minus 1, 0.
Minus 1, 0. Okay. This, okay, let me call this W. This spans W, right? Yes. Because what is, if it spans W, then any element in W can be written as a linear combination of these two elements. So if I take a linear combination of these two, what will I get?
No, but the second one will be minus 2f, right? Like, let's say you take A and B.
Ah.
So if you take A and B, the second coordinate will be minus A minus B, right? So here, but we have only minus x, right? X minus x.
X minus xz.
Yes, ma'am. So,
So what is the question?
we take A and B as we're just trying to see if the basis, right? Like which spans.
Oh, okay,
So
okay,
A
fine.
and B. So A and B, if you put A and B, minus A minus B, it will become, right? So,
you want to write this as alpha times 1 comma minus 1 comma 1.
Yes, yes, yes.
Beta times 1
Or
comma
the other way
minus
around. If you put A and B also here, it will become minus alpha minus beta is minus.
I want to find alpha and beta in terms of A and B, right?
Yeah, yes, ma'am.
Yeah. So this is alpha plus beta minus alpha minus beta alpha. So my alpha is B and
Alpha plus beta is A.
Alpha plus beta is A. So beta is A minus B. Right? So any vector in the vector space can be written as B times 1 minus 1 1 plus A minus B times 1 minus 1 0. So this is a spanning set, right? Yes, that is why I am able to write like this, right?
Yes.
Now what will happen if I remove one of these elements?
You won't be able to write vector in that way.
I won't be able, suppose I remove this element.
Ma'am, I did not get the line you have written B 1 minus and A minus.
Do you agree that any element in W looks like this?
Yes, ma'am.
Do you agree that this vector is equal to this vector?
Which one, ma'am?
This A comma minus A comma B is equal to this. Just simplify the right hand side. This is what? B minus B, B. This is A minus B minus A plus B, 0. When I add these two, I'll get A minus A, right?
Yes, ma'am. Yes, ma'am.
Yeah. So this vector is written as a linear combination of these two vectors, right?
Yes, ma'am.
And this is any general vector in W, right?
Yes.
Here, this one, x minus x, z. So do you agree that this set spans W?
Yes, ma'am.
Okay.
But I have a confusion, ma'am. In this equation, when x plus y is equal to 0, z can be anything.
Where is x plus y is equal to 0?
When you were explaining the equation W.
On above.
Okay. Z can be anything, yes.
So here we can see when we do the solution that somehow x and y is dependent to B.
No, where?
No. Okay.
It's completely
it's
different.
a basic.
Yes,
ma'am. Basic. So we have taken 1 and 0 for a Z. Both we have taken. Okay, ma'am.
The number of elements in a basis should be equal to the number of dependent variables or number of independent variables.
Number of independent variables.
Okay. But if there is a matrix which has 3 pivots, then the number basis elements will be 3 in that, right?
No. That independent, this independent is different. No?
Okay.
Ma'am, could you repeat this question because still I'm not clear on this.
Okay, so what I'm trying to do, okay, someone asked me for an example of a minimal spanning set. So I'm trying to explain what a minimal spanning set is. Okay, so for that, first I took a vector space. Is this vector space clear? It's a plane, right?
Yeah, this is clear.
Yeah, and this, the set of all vectors in this vector space can be written like this, right?
Yes.
Z can be anything. If X is fixed, Y is fixed. If Y is fixed, X is fixed, right?
Okay, and Z can be anything.
Yeah, because there is no condition given on Z.
Yeah, got it.
So the dimension of this subspace is 2, right?
Yeah.
But don't get into the details of dimension for now because we don't need a basis, but I'm just telling you. Okay. So now someone told me that this spans W. I'm just checking that.
Okay.
Okay. This is any set. I'm checking whether this set spans W. If it spans W, then any vector in W should be written as a linear combination of these two vectors, right?
Yeah.
I take any vector in W. It looks like this, right? A minus A. I'm trying to write it as a linear combination of these two vectors. Once I find out alpha and beta, I'm done, right?
Yeah.
I'm doing that. I'm simplifying. Alpha plus beta minus alpha minus beta, comma alpha.
And then substituting.
I equate and then I find out alpha and beta. Alpha is B, beta is A minus B. So
But
any vector.
How do we choose these two vectors, like these two spans W?
No, so one of you only gave me the example. I did not tell it spans. I'm just checking whether the example that you gave is working or not.
Okay, ma'am.
So this spans because any vector in W can be written as a linear combination of these two vectors.
Finally,
what is it? I did not hear clearly. Your voice was breaking.
Yeah. Finally, here we are considering the left side and right side are equal.
Yeah, I am writing this as a linear combination of these two vectors. That's it.
Yeah, whether this form is correct or not, we are.
That I verified here.
We should have taken by X, Y, Z.
Okay. A, B, C. Okay, I should have taken X, Z, right? Because Y is equal to minus X. Okay. So this is what Z. This is Z minus X. Now fine. Fine.
Yeah. Now we would be checking for minimal.
Yeah. How will I check whether it is minimal or not?
By removing one.
If I remove one vector, if it still spans, then this one is not minimal. If I remove a vector and if that set doesn't span, then this is minimal, right? So let me remove one of the vectors. Say I remove 1 minus 1, 0. So now I am left with this set, 1 minus 1, 1. Does this span W? My W is this. Set of all x comma y comma z. Such that x plus y is 0. Does this span this set?
It will be x minus x and z, right?
Huh?
X minus x and z. Otherwise.
Yeah, the set, yeah. X minus x, z. Does this set span this space?
No, no.
Yes, yes.
No.
Because
yes.
x plus y is 0. X plus y is 0 and the first is 1 and second is minus 1. So we are adding, we are getting 0.
No.
For z, we don't have any condition.
The answer is no. Can you give me one vector in W which does not belong to span of this?
Any vector, like
3 minus 3, 4. 3 minus 3, 4.
3 minus 3, 3.
0.
belongs to W, right?
Yes. Yes.
But does not belong to span of that set, right?
Yes.
Clear?
You're not able to write this with the help of the span, right?
Yeah,
Yes,
yeah.
yes.
Because span of this is what? A minus A. All three coordinates should have the same magnitude. But that is not this set, right? Z is independent. Z can be anything.
Even the other one is the same. 1 minus 1 0 also
Even if you
can't do
take the
anything.
other one.
Yeah, that also
Yeah.
not possible.
So this is a minimal spanning set.
Yes.
If I add any vectors to this set, will it still be a spanning set?
Yes.
Yeah, because these two vectors are enough. If I add, I'm just having more, right?
It's a superset of
Yes,
Yeah.
you can take 0.
You can take any vector.
Correct.
It will still
I'm
be
saying
a
yes,
spanning set.
it will still be a spanning set. I'm saying that it will still be a spanning set.
Yeah. Any superset of a spanning set will still remain a spanning set.
Correct.
Yeah. So is it clear that this is a minimal spanning set?
Yes.
Ma'am, can we take hello, span of W, can we take 0, 0, 1?
Yes.
Or 0, 0, 0. That is always
0,
always
0,
there. Always there.
That will not that can never be a spanning element,
Yeah.
right?
But 0, 0, 1 we can take that.
This is also a spanning set. This is also a basis for W, right?
Yes.
These two elements.
Okay, ma'am. Yeah. So it has to be 0, 0, 1 and 1, minus 1, 0 to span.
You can
Otherwise
put
it will
anything
not
else
span.
also here. Put 5 here, it doesn't matter.
Yeah. Just for Z it can be anything, that's why. Okay.
Okay, so this is minimal spanning set. What is a maximal linearly independent set? So is this set linearly?
Just sorry, because can we continue with this one tomorrow, ma'am? We have a meeting and it's already 10:15.
Yeah, I don't mind stopping.
Ma'am, just one like addition to this. Can't we remove the first part of it and then second would be the minimal?
You want to remove this?
Yeah.
Does 1, minus 1, 5. Can you span this element with this?
The last
No,
element
right?
will always be
Span
0.
of this will always be 0, right? The last element will always be 0, right? Span of is going to be A, minus A, 0, right?
Okay.
You said this belongs to W, but I cannot use this and get this, right?
Yeah, got it.
Yeah.
Thank you.
So it's a minimal spanning set. Can you similarly understand the concept of a maximal linearly independent set? Minimal means you cannot reduce. Maximal means you cannot add, right?
Yes.
To add it will become dependent. Sorry. Yes.
Yeah. And a basis is nothing but a minimal spanning set, which is also a maximal linearly independent set. Okay, then we'll stop here.
And then,
Tomorrow?
And then we can say that basis is a subset of a spanning set, right?
Basis is a spanning set, yes.
This is a subset of a spanning set. We can say that, right?
Yeah. But it depends on what you mean by subset. See, there are infinitely many bases for a vector space, right?
Okay.
Yes, ma'am.
Yeah. So you cannot tell that if you can see. This is a basis for W.
Correct.
This is a spanning set for W, but this is not a subset of this, right?
Correct. It may or may not be. It may or may not be.
No, in what sense you are asking? That also matters.
No, okay.
In some sense, it is right.
I'm saying, ma'am, say for example, there are 3 elements in my spanning set, right? And those are basically superset, right? So if I take only 2 elements out of those 3 elements, then I will get a basis which will still be spanning my vector space. So in that case, I can say that basis is a subset of spanning set.
Yeah, like I understand what you're trying to tell, but that's not the right way to put it. What you
Okay.
can tell is you start with the basis.
Yes.
Any superset will be a spanning set. You can tell
Yes.
that.
Yes.
Yeah.
Any superset will be a spanning set. So
Yes.
now, now, ma'am, this brings to me my second question. Like with the help of my sorry, with the help of basis also I can span my vector space, and with the help of spanning set also I can span my vector space, right?
Yes. Yes.
Then what is the utility of a spanning set? When I can do the same work with the help of basis, then what is the utility of my spanning set?
See, you have the concept of spanning set first, then comes the basis. So what happens is a lot of elements can be in spanning set. You
Okay.
throw out all the unwanted elements and bring it to the smallest form possible.
Okay.
Lesser than which is not enough for me. That is what is a basis. That is why this concept of a minimal spanning set.
Okay, okay. So we have come to the definition of basis with the help of a spanning set, right?
Yeah. See, in R2, give me a basis for R2.
1 0 and then 0 1.
Yeah. So this spans R2, right?
Right, ma'am. Yes.
Does this span R2?
Yes. Yes. Yes.
Does this span R2?
Yes. Yes.
But these are all unwanted, no?
Correct.
Yeah, so that is why I remove it and bring it to the minimal spanning set.
Okay, so what I said earlier, I can modify my statement and I can say that all superset of basis is my spanning set, right?
All supersets of a basis. Yes. Yes.
I can modify my statement and I can say like this, right?
Yes. Yes.
Ma'am.
Yes.
If possible in discourse, you can post this like Ax equal to B. In video lecture, professor has proved with the help of determinant, right? But we know that determinant exists only for a square matrix. Yeah. So how to prove this for a rectangular matrix also? But I'm not getting.
What do you want to prove?
Ax equal to B. This relationship Ax equal to B. Professor has given a proof, but he has done this using taking the help of determinant, right? But we know that
proof of what I'm asking.
Ax equal to B. Ax equal to B. Professor in the video lecture has given a proof for Ax equal to B.
No, how will you prove Ax is equal to B? Like,
he has done this now. I won't be able to explain right now. He has taken the help of determinant and then A into A inverse like this.
Okay, why don't you post that lecture reference in discourse and ask? I'll answer there.
I'll do that, ma'am.
Yeah.
And now one more thing, in your last video lecture, you were saying something and I could not understand the meaning, that you all felt very bad, for quiz 2, and then there will be something, in quiz 3.
Feedback, there was a feedback, huh?
Oh no, yeah. So the feedback said that it didn't test the knowledge. So
ma'am, that was incorrect. It was because the questions in quiz 2 were conceptual, and it do test the knowledge, because if you have not prepared well for quiz 2, then you won't be able to attempt that paper well.
Yeah. Okay, yeah.
So
that is what some others posted on discourse. Yeah, if you had studied, anything would be easy, no?
Yeah.
It was like that. Yeah.
Okay, so few students have given the feedback that it was too easy, right?
Yeah. Too easy doesn't matter, but there was a comment which said that it wasn't a paper enough to test the knowledge of the contents.
I don't agree, ma'am, because see, the knowledge which we get from the from the weeks of quiz 2 during the preparation, that knowledge only we applied and we gave that paper, and then only
will it have some negative impact on end term?
No, definitely not. We want to make sure that nobody feels bad that the quality of the paper was low. After all, you're giving an exam for an IIT.
It should not happen that we are struggling to get 40 marks also.
No.
True. This is a fair, man.
Okay. So shall we stop the session in the sense of contents?
Yes, ma'am.
So tomorrow
what is left for week 4?
Basis, just the definition of rank came in week 4, right? So I'll ask Shubhajit to start from basis tomorrow.
Okay, ma'am. Tomorrow what time, ma'am? Because it is not there in the
it is there 7 p.m.
7 p.m. 7 p.m.
Acha, 7 p.m. Okay.
Ma'am, who will be there? Shubhajit sir.
Yeah.
So, ma'am, 7 p.m. that is week after 4, na? 5, 6, 7.
No, tomorrow.
5 to
Yes,
7.
tomorrow.
No.
Tomorrow.
Week will be taken is 5 and to 7, na?
5,
4
to 7. 4 to 7.
5 to 6, no? I thought only 2
5
weeks.
to 7.
5 to 7 tomorrow.
Okay. Anyway, we have enough sessions to cover.
And we just have 2 more sessions. Are you confident?
Thanks a lot.
3 more, right?
2 more.
There's one tomorrow.
Can
No,
we
3 more,
complete
3 more.
before our
3
first
more.
mock test,
If-
ma'am? Can we complete before our first mock test? 30th
When
is
is
the
mock?
first.
It's on
First
27th,
mock.
right?
No, ma'am,
Even
it is on 30th.
one is there on first.
30th
There
is
will be a
mock, is it?
single mock, right?
Yes,
Monday,
ma'am.
Monday, there is a mock.
28th.
Where do you see that mock test
28th, yeah,
details?
Monday.
Where do you see the mock test details?
And we cannot see on 27th any mock.
No
Is
mock.
it
Okay,
there?
wait.
On
No,
28th.
we received an email just now sometime back. It's on 28th. That's what they said.
Oh, okay, fine.
Where
Okay.
where is the information on the mock test?
There's an email.
There is an email today. Yeah.
Don't
Email.
post it on the
At
calendar.
around 11 o'clock.
Oh my god.
8 p.m.
No, they sent an email at 11 o'clock today. The
8
mock
p.m.
is on 28th at 8 o'clock.
Evening 8 p.m.
Anyway, the mock will be available always. So even if you can't attempt it at the
It is a
time of
timed
mock, you
ma'am.
can
It is a
attempt it.
timed mock.
If you attempt it at 8 o'clock, it will be timed mock. Otherwise, you can attempt it at any point.
8 to 9:30.
But this is not graded, is it?
No.
Mock
No,
will be
okay.
graded.
But that will not be taken off after the time, right? Like the earlier it used to happen now, one of those mocks is only for the time being, not be available.
No.
This
That
not be
was
like that,
graded.
right?
That is why it was like that.
Okay. Thanks.
Sorry.
Okay, fine.
Do we get
So-
the mock solutions?
Yeah, we will put the
Okay,
solutions
we get
after the mock is
solutions?
over. After the timed mock is over, we'll put the solution.
Okay.
Okay, ma'am. Thanks a lot. Thank you.
Yeah,
Thank you,
okay.
ma'am.
So tomorrow
Thank you,
from
ma'am.
which?
So 5th week to 7th week, is it not tomorrow?
I'll ask him to start from basis. Basis of
Yes.
the vectors.
Okay.
Thank you so much, ma'am. Thank you.
Thank you very much, ma'am.
Thank you.
Very informative class.
Thanks, ma'am. It was great help.
Thanks, sir. Thank you.
And tomorrow 5 to 7?
No, 7 o'clock.
7
Tomorrow's
o'clock.
session
7
starts
o'clock.
at 7. Yes.
Okay.
Weeks 5 to 7.
Okay.
Yeah.
Thank you, ma'am.
Yeah, thank you.